What if I told you that teleportation is already real? Not in some distant science fiction future, but right now. And it's not just happening in a lab, it's being quietly tested on the very internet you're using at this moment. Now, before you start yelling, "Beam me up, Scotty," let's get one thing straight. This isn't the stuff of Star Trek. We're not beaming people or physical objects from one place to another. We're teleporting information. And this breakthrough is on the verge of changing everything you know about online privacy and security. For decades, the idea of sending quantum information through the same fiber-optic cables that carry our emails, videos, and financial data was considered flat-out impossible. The belief was that the delicate quantum signals would be completely drowned out by the noise of the classical internet. But in late 2024, a team of engineers at Northwestern University did the impossible. They successfully demonstrated quantum teleportation over a standard 30-kilometer-long fiber-optic cable that was simultaneously carrying high-speed internet traffic. This wasn't a simulation or a sterile laboratory experiment. This was real-world proof that the quantum internet can be built on the very foundations of the web we already have. And it signals the beginning of a new era, one where our digital lives could become fundamentally unhackable. To understand why this is such a game changer, you first need to know a deeply unsettling secret. The entire security of our modern world is built on a ticking time bomb. Every time you send a private message, log into your bank account, or buy something online, your data is protected by encryption. This encryption works because classical computers are terrible at solving certain mathematical problems, specifically factoring enormous numbers. It would take the most powerful supercomputer today billions of years to crack a standard encryption key. So, for now, your data is safe. But a new kind of computer is coming. A quantum computer. And for a quantum machine, factoring those massive numbers is trivial. It's a puzzle they are uniquely designed to solve. Companies like Google, Microsoft, and IBM are in a race to build a fault-tolerant quantum computer, with some aiming to have one running by 2029. The moment they succeed, nearly every encryption system we rely on will become obsolete overnight. Every password, every financial transaction, every government secret, and every private message ever sent and stored could potentially be cracked wide open. This isn't some far-off theoretical threat. It's what cybersecurity experts call the quantum apocalypse. The race is on to find a new way to secure our data, a method that doesn't rely on math problems a quantum computer can easily solve. We need quantum-proof security. For years, a leading candidate has been a technology that sounds like it was pulled from science fiction: quantum teleportation. The challenge has always been the infrastructure. Building a separate, dedicated fiber network just for quantum signals would cost trillions and take decades. It was widely assumed that a quantum internet would have to be built from scratch. This is the exact problem that the researchers at Northwestern just solved. Their work proves we don't need a new internet. We can build the quantum internet right on top of the one we already have. So, how in the world do you teleport information through a busy internet cable? The answer lies in one of the most famously bizarre principles of quantum mechanics, a phenomenon Albert Einstein colorfully dismissed as spooky action at a distance. He was talking, of course, about quantum entanglement. Imagine you have two cosmic twin particles, or qubits, that are fundamentally linked. They are created together and share the same quantum state. Now, you separate them. You can send one to the other side of the room or the other side of the galaxy. It doesn't matter. The instant you measure a property of one particle, its twin instantly reflects that property, no matter how far apart they are. If one spins left, its twin instantly spins right. They are a single system, connected by an invisible thread. This connection is what makes teleportation possible. Let's build a simple teleportation machine with the classic characters: Alice, who wants to send a quantum state, and Bob, who will receive it. First, you need a pair of these entangled particles. Let's call them qubit A and qubit B. We give qubit A to Alice and qubit B to Bob, who are at opposite ends of that 30-kilometer fiber-optic cable. Now, Alice has a third particle. We'll call it qubit C. This is the particle whose quantum information she wants to teleport. Qubit C has a specific, delicate quantum state, a precise spin or polarization that she wants to send to Bob. The catch is, according to the laws of quantum mechanics, she can't just look at qubit C to see its state and then tell Bob what it is. The very act of measuring a quantum state destroys it forever. This is known as the no-cloning theorem. You cannot create a perfect copy of an unknown quantum state. So, instead of measuring it, Alice performs a different kind of measurement, called a Bell state measurement. She takes her entangled particle, qubit A, and the particle she wants to teleport, qubit C, and measures them together. This joint measurement does two things. First, it destroys the original state of qubit C, ensuring no copies are made. Second, it generates 2 bits of classical information, just regular ones and zeros. This is the teleportation moment. The instant Alice performs her measurement, the quantum state of qubit C vanishes from her location, and, thanks to the spooky entanglement linking A and B, the information needed to reconstruct it is imprinted on Bob's particle, qubit B, 30 kilometers away. But the state on Bob's qubit is jumbled up. It's like a locked message. To unlock it, Bob needs the key. That key is the 2 classical bits of information Alice generated. Alice sends these 2 bits to Bob over a classical channel. It could be an email, a text, or just a light signal down the same fiber-optic cable. This part isn't instantaneous. It's limited by the speed of light. So no, quantum teleportation doesn't break the laws of physics or allow for faster-than-light communication. Once Bob gets the 2 bits, he knows exactly which of 4 operations to perform on his particle, qubit B. It might be a bit flip, a phase flip, or nothing at all. He applies the operation and his qubit transforms into a perfect, identical replica of Alice's original qubit C. The information has been teleported. The original has been destroyed. A perfect reconstruction has appeared somewhere else, without ever physically traveling the distance between them. That is the essence of quantum teleportation. If your mind is bending a little right now, you're in good company. We're brushing up against the fundamental weirdness of reality. But if you want to stay ahead of the curve on how these technologies are actively reshaping our world, make sure you subscribe and turn on notifications. Because what we're about to explore next isn't just theory, it's the blueprint for the future of your privacy. So, what does this mind-bending process have to do with protecting your data from a quantum computer? Everything. This kind of teleportation is a critical building block for creating secure quantum networks, enabling powerful technologies like quantum key distribution or QKD. This offers a form of security that isn't based on mathematical difficulty, but on the unshakable laws of physics. Let's go back to Alice and Bob. Imagine they want to have a secure conversation. They need a secret key, a random string of ones and zeros that only they possess to encrypt and decrypt their messages. Classically, distributing this key is the most vulnerable part of the process. If a hacker, let's call her Eve, intercepts the key, the entire communication is compromised. But by using quantum entanglement, the game changes completely. Alice and Bob can generate a secret key using entangled particles. Now, what happens if Eve tries to intercept these qubits as the entangled connection is being established? Here's the beautiful part. She can't do it secretly. The moment an eavesdropper tries to measure or even observe an entangled particle, the delicate quantum state collapses. That spooky connection between the twins is disturbed in a way that is immediately detectable to both Alice and Bob. They would instantly know their channel was compromised and abort the key exchange. Eve can't spy on the key without leaving an unmistakable trail. Hacking is no longer a matter of having a faster computer. It becomes physically impossible. This provides a truly unhackable line of communication. The breakthrough from Northwestern University proved that this process can work even in the chaotic environment of a live internet cable. For years, researchers thought the millions of photons from classical internet signals would create so much noise that they would instantly destroy any delicate quantum signal. It was like trying to hear a pin drop in the middle of a rock concert. But the Northwestern team, led by Professor Prem Kumar, found a way to navigate the traffic. They discovered that by carefully choosing the wavelength for their quantum photons and using specialized filters, they could create a quiet, protected lane within the noisy fiber, allowing the quantum information to be teleported without interference. They successfully teleported quantum states over 30 kilometers alongside massive streams of data, proving that quantum and classical communication can coexist in the same infrastructure. As Professor Kumar put it, this is incredibly exciting because nobody thought it was possible. This discovery is a total game changer. It means we don't have to choose between the classical internet we have and a future quantum internet. They can be one and the same. This dramatically lowers the cost and complexity of building a secure quantum network by leveraging the billions of dollars of fiber-optic infrastructure already crisscrossing the globe. This brings us to the ultimate implication of this research, the birth of the quantum internet. It's important to realize the quantum internet won't replace the classical internet you use for browsing, streaming, and social media. Instead, it will act as a parallel layer, a secure backbone running on the same physical cables. Think of it as an encrypted express lane built right alongside the main highway. This network will do far more than just secure communications. Its primary function will be to connect quantum computers, allowing them to work together in ways that are impossible today. Right now, quantum computers are mostly siloed machines. Building a single machine with the millions of stable qubits needed to solve world-changing problems is an immense engineering challenge. But the quantum internet changes that calculation. By using quantum teleportation to link smaller, less powerful quantum processors across a city or even a continent, we can create a single distributed quantum computer. This network would pool their computational power, allowing them to tackle problems in drug discovery, materials science, financial modeling, and climate change that are far beyond the reach of any one machine. Furthermore, a quantum internet will revolutionize sensing. Imagine a network of entangled sensors acting as a single planet-sized observatory. This could be used for everything from improving earthquake detection and tracking gravitational waves to creating hyper-precise navigation systems that don't rely on vulnerable GPS satellites. This isn't a distant dream. The building blocks are already being put in place. In the Netherlands, researchers are building an entanglement-based quantum link between cities like Delft and The Hague. In the U.S., projects in Boston and Chicago are creating metropolitan quantum networks, and with the recent breakthrough showing this technology can run on existing fiber, the pace of development is set to explode. The United Nations has even designated 2025 as the International Year of Quantum Technology, signaling a global focus on turning these scientific achievements into practical applications. We are at the very beginning of this new technological revolution, much like the early 1990s with the classical internet. The first connections are being made, the first protocols are being written, and the immense potential is just starting to come into focus. Quantum teleportation is no longer science fiction. It's real, tested, and moving from the lab into the real world. Scientists have shown quantum communication works on today's fiber-optic cables, bringing the quantum internet closer than ever.